part 2 of this lesson now. This is the part that I've been using every day. I would love to show you some of my equations, but my kids tell me that it might scare you, the exponential growth that we see. But by the end of this, I might go ahead and show you some of them. This is an example of where we come up with the equations for exponentials. In this example, it says in 1983, there were 102,000 farms in Minnesota. But by 1998, this number had dropped to 80,000. Now, the first thing that you will notice is we can make these ordered pairs. So there are 2 ordered pairs. Now, the key is when you're using years, we don't want to use 1983. We want to use that idea of 0. When did we start this? And that's what I'm learning with the coronavirus when I'm looking at how it increases each day. The numbers at the beginning, because they're so small, I'm not able to use those in the same way that the numbers when they become more consistent are. So before 1983, maybe this study wouldn't have worked, but we're talking about 1983. So we're using the idea of 1983 as our 0. So in 1983, year 0, the year the study started, there were 102,000 farms in Minnesota. By 1998, there were 80,000. Now, we're not going to put in 1998. We're going to think of the idea, if 0 was 1983, how many years later was 1998? So that value would be 15. So when I'm doing this, I'm using the day as when it started as 0, and then I can write an equation on any day after that based on how many days later that was. Sometimes it's hours. Sometimes with bacteria, when you're talking about bacteria, you're talking about hours. But again, in this case, we're talking about years. So it says, write an exponential function that can be used to model the farm population Y of Minnesota. Write the function in terms of X, the number of years since 1983. Here's our 2 ordered pairs. Now, very similar to Y equals mx plus b, we can write an equation. So if I used Y equals mx plus b, let's take a look at that real quick. If I used Y equals mx plus b, there would be 3 steps. We would find slope, we would find the y-intercept, and then we would write the equation, which, by the way, we can do with this data. I can find the slope because the slope is y2 minus y1 over x2 minus x1. So that would be y2, 80,000, minus 102,000 over 15 minus 0. I'm going to sneak back and get a calculator real quick. So if I take 80,000 minus 102,000, I get negative 22,000, 15 minus 0. And it looks like the slope is about negative 1,400. We'll round it off to the nearest whole number here. Then we can find the y-intercept. So the y-intercept, y equals mx plus b. I'm going to use that first ordered pair. Y is 102,000. M is negative 1,467. X is 0. B is 102,000. So my equation is negative 1,467x plus 102,000. This is called a linear model. That's a linear model. That is what happens if every year we lose the same number of farms. We started with this value. Every year, the number of farms is decreasing by almost 1,500. That's a linear model, but we know not everything does linear. It might not look like that. It might decrease quickly and then start to taper off at the end. So we are going to write an exponential, but it's similar. This is the equation that we want. So we need to find A and we need to find B. So when you find A, I'm going to show you one time how to find A, and then you're never going to have to find A again. Because to find A, I'm going to start out by plugging in this first equation. Y is 102,000. A, we don't know. B, we don't know. And X is 0. Anything to the 0 power is 1, which means that just cancels. And A is 102,000. This is our A value. It's the starting point. It's patient 0. How many did we start with? How many farms did we start this study with? How many bacteria did we start with? How many zombies did we start with? How many people were infected? How many mice did we start with? That's what your A is. A is just going to be that value. Okay, so we now know A is 102,000. So we need to use the other point. Now we use this one to find B. And we're going to plug in to this equation again. So Y is 80,000. I'm going to make this bigger again. Okay. So now Y equals AB to the X power. So Y is 80,000. We now know that A is 102,000. We're looking for B, but X is 15. So we need to solve that variable for B. Just like we solve any other equation, we need to get rid of this first. Oops, I keep doing that. So I'm going to start out by dividing. Now that's going to be a tiny number. So 80,000 divided by 102,000 is, we're going to round it to 0.784. And that's equal to B to the 15th power. You can actually find the 15th root of that. Okay, so we can take the 15th root in the calculator. We type in 15 first. Then we do our second button that looks like this. And then we can type in the 0.784. And it looks like our B is approximately 0.98. So that is our B value. So our equation is Y equals 102,000 times 0.98 to the X power. And that's decay. 0.98 is less than 1, so it is decay. Now this last question says, if this continues to decline at the same rate, estimate the number of farms in 2012. Let's change that. Let's change it to 2020. How many farms in Minnesota are there? Well, here's the equation. Y equals 102,000 times 0.98 to the X power. X is the number of years since the study started when there were 102,000, which is 1983. So our X value in this case is going to be 37, was since 1983. So I can plug this in to the calculator, 0.98 to the 37th power, and we get around 48,302 farms. Significant drop from the 102,000 37 years ago. But here's the thing about exponential decay. If it was linear, what eventually happens in a linear is that it's eventually going to equal 0. I don't know, unless there's an apocalypse that happens, that there's ever going to be no farms in Minnesota. But in an exponential, it drops, but it never hits 0. And that's what an exponential function is. That's what we do with exponential functions. And that's what we're looking at. And that's what I do every day at 2 o'clock when I watch Dr. Amy Acton and Mike DeWine. I write an equation. I have lots of equations for predictions of how many that there new cases there will be. So that's part 2. We still have another part to this first lesson though.